Hello. In this section, I will talk about the extreme values. Extreme values are basically a maximum or minimum values of the function or of any like objects or any situation. That means, for instance, when we will look a little bit at the real world scenario situation, we always talk about some extreme values, maximum or minimum. For instance, we can talk about the tallest person or shortest person. We can talk about the longest distance and the shortest distance, largest item and the smallest item. We can always talk about some extreme values, right? Okay, that's me. Let's try to define this more explicitly, like how we can actually find out and define these extreme values. Before we start, one important thing. I have to mention one important thing, because talking about, for instance, the tallest person, are we looking at the tallest person, let's say, in the class, or are we talking about the tallest person on the earth or in the universe? Yeah, depends how globally we're looking. Yeah, or for instance, we're looking at the brightest like item in the box, or we looking the brightest item on the earth. That means we will have two types of extreme values. We will call locally highest or lowest value and globally highest or lowest value. Actually, globally, we will call absolute, like absolute maximum or absolute minimum. Locally highest or lowest value, we will call local, maximum or minimum. That means let's distinguish the difference and let's define both of them. Okay, looking at the graph of this function, this is function f of x, we will identify both local and absolute extreme values. That means let's assume that function is defined from a, yes, this is function f of x. That means let's say f of x is defined on the interval from a, and let's maybe call it let's call it f. Let's amend a little bit. That means this will be x, and this is f. Okay, that point is f. That means function is defined on the interval including a and f. Okay. And now what we see, when we will look, let's look globally. Let's look for the absolutely highest point and absolutely lowest point, because this is a little bit easier. We're looking at the x value, that the corresponding y value is the highest. Everything else is below. That means we may notice that this point, which is the value at d, f of d, is absolute maximum. Because all of the other values, when I take a couple of x's near, or even I can take any point between a and f, the corresponding value will be less than f of d. Okay? Which means f of d is the highest point, absolute maximum. And now I think the lowest point is f of a. Yeah, this will be absolute minimum. Okay? Because if I will pick any value, for instance, I can pick this one, and of the value of, let's say, g. Right? That means the value of the function at g, f of g, is definitely higher than f of a. That means f of a is minimum. And actually, I can pick any number from the interval from a to f, and the corresponding value will be higher than f of a. F of a is the lowest point. Okay, that's when we have absolute minimum, absolute maximum. But now let's look at closely, and let's maybe look more locally. When we look at the value f of b, this is f of b. Now, when I will narrow the search for the values just a little bit on the left and a little bit on the right-hand side, theoretically creating like a neighborhood of b on the left and on the right-hand side, b is inside that interval. We can see that blue interval. Then, if I will take any values, we can see this value is lower than f of b. On the other side is lower. Looks like b is the highest point. And we may also notice at b, I can draw horizontal tangent. Yeah, because that's also important characteristic. That means b looks like it's the highest point, but locally. We will call local maximum. Okay, B is local maximum. We can also notice that D, I know that D, f of D is an absolute maximum, but when we look locally, yeah, if I will take a couple of values on the left and on the right-hand side, which that's the blue dots corresponding on the left and on the right, these values are lower. That we can also call that f of D is a locally highest point, local maximum. It could happen. Absolutely highest point could be also a locally highest point. Okay, and we can also draw horizontal tangent. Actually, horizontal tangent, slope of a horizontal tangent, yes, slope of any horizontal line is 0, but we can define slope in terms of calculus as derivative. That we can say that derivative at the point B is 0. Derivative of the function at the point D is also 0. Okay, yeah, that's we actually trying to look at a couple of characteristics. Okay, now we still have point f of c. We can see f of c here. Looks also like locally, when we look at the neighborhood locally, all of the values above on the right and on the left-hand side, yeah, actually they are above, they are higher. That means all of the values for the corresponding axis from the left and the right-hand side at C, they are higher than f of c. Then we can say that f of c is also local, but in this situation, minimum, local minimum. F of c is locally lowest point, just locally. Yes, we're not going far. We know calculus, we are really near to the point. Here, we do not have horizontal tangent. However, we have this corner or cusp, and we know that derivative does not exist, dne. Okay, that means at C, derivative does not exist. Okay, we also have locally lowest point at E, because when we take a neighborhood, an interval, that E is inside this interval, and we will check a couple of points on the left and on the right-hand side, the values are above. This is the lowest point, and actually horizontal tangent. That's we can say f of E is locally lowest point. Locally lowest point, and the derivative at the point E is 0, because we do have horizontal tangent. Slope of a tangent is derivative, and horizontal lines has a slope 0. Okay, that's we have, let's put this nicely together. We have a definition, almost a definition of a locally, at which value of x function will attain local maximum or local minimum, and also absolute maximum, absolute minimum. I think one point left, this one, yeah, which actually f of f. I know sounds weird, but f is the value, this function, and f is the other f inside is the x value. That means this point, it's not the highest, it's not absolutely highest, absolutely lowest. However, we may think is locally highest. But based on the definition that I will provide in 1 second, we cannot call this locally highest point, because we don't know what is happening on the right-hand side. Even if domain ends, that we don't know. That we know that when I take the points on the x values on the right, on the left-hand side, they are lower. Yes, we can see lower. This is highest, but we don't know the right-hand side. We don't know the neighborhood. That means f of f is neither, it's not a locally highest point, and it's not absolutely highest, but that's obvious. Okay, That's based on this graph, we identify local extreme values and absolute extreme values. Let's look at the definition. Okay, that means absolute extreme values are the highest point on the graph at the lowest point. And we can see if we will say that function has absolutely highest point at c, then f of c will be greater than f of x for all of the x's in the domain. If we will say that function has absolute minimum at c, then value at c is the lowest value because all of the other values f of x for all of the x's in the domain are greater. We can see this. We can see this relation. Okay. Now, locally, yes, locally we have to be a little bit careful. Function f has a local maximum, or sometimes we may call it relative maximum. At c, if c, we can see values at c, f of c is greater than f of x when x is near c. Mathematically saying is c is placed in the open interval, which means C we have to check the values of x on the left and on the right hand side. C must be placed in the interval, and then we can check the other values. We may the other x's, and they have to be lower, and respectively for the local minimum. Function f will have local minimum or relative minimum at c if f of c is smaller than f of x for all of the other x's near c on both sides. C must be placed in the open interval, like we did have on the graph. Okay, that's the definition of the absolute extreme values, and this one is local extreme values. And for instance, example number 1. Looking at the function x squared, let's identify absolute extrema, and local extrema. Okay, we can definitely see this is the lowest point. And it looks like at 0, yes, at x0, the value is also 0. I mean, we cannot be confused. That's x value, and this is the y value. That means 0 is definitely a lowest point, absolutely lowest point. It's, I cannot write this, is f at 0. Okay, that's absolutely lowest point. And we can also notice that this point satisfies the local 0 is in the open interval. And then we can also say it's a local minimum value. Yeah, that means it's an absolute and the local. And the value actually is 0. Can I write here? It's 0. Okay, but we know that function x squared goes up to the infinity. That means highest point, absolutely highest, and locally highest does not exist. Beautiful. And also, let's look at this calculus feature. In this situation, a function is differentiable everywhere, then derivative at that 0 is actually 0. Yes, we can say horizontal tangent. Yes, slope 0. Okay, good, because that's important characteristic. Let's look at the example number 2, x cube. And actually x cube, we remember, has at 0, it's interesting actually function. Function has a horizontal tangent. Horizontal tangent. Yes, because we know that derivative at 0 is 0, and 0 is in the domain. But this function behaves like this, is increasing horizontal tangent and then again increasing. That's we do not have this situation of maximum locally highest or lowest point. Basically, this function is strictly increasing, then its function doesn't attain local extreme values and also the absolute extreme, because function is going up and from negative infinity to positive infinity. That means absolute extrema doesn't exist and local extreme values, they don't exist. That's means please remember x cubed. Yes, and if we think, yes, where function has a horizontal tangent, this is x cubed, let's maybe do explicitly, we need to find where the derivative is 0. Derivative is 3x squared, and derivative is 0 if 3x squared is 0. 3x squared is 0 if x is 0. That means at 0, it's definitely derivative at 0 is 0. Yeah, because that's x value and this is y value. That means at 0 is horizontal tangent. Because slope, yes, this is horizontal tangent. Yes, slope is 0. Let's say f prime at 0 is 0. Yes, this is that 0. Yes, but we may also notice, actually, even if we have horizontal tangent, local minimum maximum does not exist. Okay, interesting example. Let's look at the example number 3. Beautiful sine curve. Yes, we notice this. That means this is definitely sine function, sine of x. Everybody recognize this. And now, absolutely highest, absolutely lowest point. We can see 1, negative 1, 1, negative 1. That means absolutely lowest point is negative 1, absolutely highest point is positive 1. And now we have to be really careful because this always absolutely highest or absolutely lowest point must be just one exact value. We cannot say this function has infinitely many absolute minima or absolute maxima. No, it's happening infinitely many times, but the value itself is only one because we can only have one highest value. We cannot have two highest values or respectively lowest values. Okay, that means, for instance, 1 is happening at pi over 2. We can see it's happening at 5 pi over 2, or it's happening at negative 3 pi over 2. Am I right? Negative 3 pi over 2, and so on. Yes, every 2 pi the situation repeats. But what is the corresponding value? It's basically 1. Now negative 1, it's happening at 3 pi over 2, is happening at 1, 2, 3, 4, 5, 6, 7 pi over 2, which actually I can just add 2 pi. Okay, or it's happening at negative pi over 2, and so on. And that we can see it's happening infinitely many times, but the value itself, the minimum value, is negative 1. It has to be a lot. Please remember. Okay, and now I believe these values are also satisfying a local extreme value definition, because like we can see, this is locally highest. Pi over 2 is definitely we can place in the open interval. We can check all of the other values on the right and the left-hand side are lower. That means this is also 1 is a local, actually negative 1. 1 is a local maximum and negative 1 is a local minimum. And since function is differentiable, horizontal tangent, horizontal tangent, horizontal tangent at these points. And also the same thing can happen infinitely many times, but the local maximum is 1. Absolute maximum, the same 1. Local minimum, negative 1. Absolute minimum, negative 1. Okay, and now example number 4, absolute value of x. Similar to x squared, yes? I mean, we do have a big difference, but similar to the values. We can see the lowest point. That means f of 0 equals to 0. This is the absolutely lowest point. That means f of 0 equals to 0. And also that x equals to 0 is placed in the open interval. All of the values on the left and the right hand side, they are higher. That means this is locally lowest point. F of 0 is 0. No absolute maximum and no absolute, no local maximum, no maximum values, okay? But in this situation, derivative at 0, yes, this is that 0, actually it's not 0, derivative does not exist because function is not differentiable, sharp corner, yeah? So we can see this, also good calculus characteristic. Okay, and then one more, cube root of x squared, also one of the functions that we supposed to know. If you watch section 1.1 graphs, you definitely know what we're talking about. That's the graph. We know that this looks like a locally lowest point and absolutely lowest point. That means this is again mini. Okay, oh, too fast. Let me write f of 0 equals to, oh, I cannot write 0, and locally lowest point. Yeah, this is that 0. No highest value, absolutely, and locally. And for the calculus characteristic, derivative at 0 does not exist. We cannot draw horizontal tangent. Function has that sharp turn, cusp or kink, we can call it, and we know that derivative does not exist. Function is not differentiable. And that's a good characteristic. Okay, that's me now. Let's put this together. Local extreme values. Okay, that means the crucial observation that we did, yes, is for differentiable function, nice and smooth function, differentiable function at x equals to c, the tangent line at this locally lowest or locally highest point, locally lowest or locally highest, is always horizontal. Then derivative at that point c is 0. Otherwise, when function has this sharp corner, cusp, kink, the tangent line may not, actually does not exist, then the derivative is undefined. That's two important observations. And now, to take both possibilities into the account, we defined the notion something like critical points. Okay, that means these c values, yes, wherever tangent line is horizontal, yes, now let's go the other way. Wherever the tangent is horizontal or wherever the derivative does not exist, horizontal tangent means derivative 0. Then at these points, if we solve, yes, if we solve this, this will be c, let's say c sub 1. Let's say the solution will be maybe c sub 2, and the solution will be c sub 3. Yeah, I can even say c sub 1, c sub 2, c sub 3, c sub 4. That means this one is actually 4. Okay, that's perfect now. Okay, that means wherever function has a horizontal tangent, we will go through this, and wherever derivative is undefined, we will go through this equation. We can find the corresponding c values, and these c values are critical points. Okay, that means they are critical points. That was our observation. And now at critical points, function may have locally highest or locally lowest point. Okay? We're just talking about the local extreme values. Okay. Now let's look at this critical numbers, the definition, the other way. A critical number of a function is a number c in the domain, of course, of the function f such that either derivative is 0 or derivative is undefined. That's it. And we know how important are the points where the derivative is 0 and where the derivative is undefined. They are critical numbers. I also have this Fermat's theorem. If function has local maximum or minimum at c, then c is always a critical number. Okay, because that's what we did. We found points where function had local maximum, local minimum at these points, and these points, these values are called critical numbers. But please notice that the converse of this theorem is not true. If function has a critical number, yes, if function has a critical number at C, then we don't know. Sometimes function may not have local maximum or minimum. And we did an example. Let's look at one more time. Okay, x cubed is a good example because derivative is 0 when x is equals to 0. But at 0, function doesn't attain maximum or minimum, local maximum, local minimum. That means this will be always a good counter-example. Okay? But if derivative is 0 at that point, or derivative is undefined, then we definitely can call that point critical number. That means this is critical number. Critical number because derivative at that 0, too fast, equals to 0. Yes, but no extreme values. It could happen. That's mean one more time, this is the definition. If we are asked to find these important numbers, these critical numbers, we have to find out where the derivative is 0 and where the derivative is undefined. Okay, that means this is the purpose of this, yes, of this session. Of course, the extreme values, we have to identify the highest and the lowest point, yes, absolutely highest, absolutely lowest, and we have to identify the locally lowest and the highest point. Yes, we can do this. Based on the graph is not a problem. Yes, but we will always start with a critical number because that was the main characteristic, yes, for the locally highest or lowest point. Derivative was 0, horizontal tangent, or derivative was undefined, cusps, king, and sharp corners. Okay, and let's finish this session with one more exercise. Let's find a critical number or numbers of this function. And this is the graph, yes, of course, we don't have to know that's not a standard graph, but we may notice that at 1, yes, at 1, function will have, as we can see, value at 1 looks like a local minimum value, but I am only taking this from the graph. The next one of the next section, the next video, will talk about more explicit way how to identify locally lowest or highest point from the formula. Now I just took, yes, I don't know this value, we don't have to know, but it's happening at 1. That means probably 1, not probably, most likely 1, x equals to 1 is a critical number. Because if function has local maximum and minimum at 1, that value 1 is a critical number. But let's find it explicitly. How we can find out, because we will not always see the graph. And maybe we have more critical values. Yeah? You probably see another 2. Okay, first of all, we're looking at the function cube root of x squared minus 2x. Yeah, that means please be really careful because in order to answer this question, find the critical numbers, we will always follow the same steps. Okay, find the critical numbers. Cube root. Domain, because we have to start with the domain. Domain is not a problem because cube root can take all of the numbers. That's we good with the domain. If we get the numbers, all of them are in the domain, all of them can be considered as a critical number. Okay, and we remember for the critical number, possibly, we have to check the derivative. Derivative must be 0, yes, horizontal tangent, or derivative is undefined. That means let's find the derivative. First of all, let's find the derivative. derivative of this function is cube root, yes, cube root of x squared minus 2x. I can maybe rewrite this function as a quantity x squared minus 2x to the power of 1/3. Let's find the derivative. 1/3 quantity x squared minus 2x to the power of negative 2/3, because I'm subtracting 1, times the derivative of the inner function, 2x minus 2. Okay, let's simplify, because we never leave the answer with the negative exponent. 1/3, 2x minus 2 will go up, and quantity x squared minus 2x will go down. And it's cube root of the quantity squared, but I can rewrite like this. Okay, that means this is a good form of the derivative. We always want the fraction. And now, one more time. Derivative is 0 if the numerator is 0. I mean, any fraction is 0 if the numerator is 0. Numerator is 0. Numerator is 0 if 2x minus 2 is 0. 2x minus 2 is 0 if x is 1. Yes, adding 2, dividing by 2. 1. 1 is in the domain. And yes, this is a critical number. We actually knew it. We knew it from the graph. That means x equals to 1 is a critical number. Now let's check where the derivative is undefined. Fraction is undefined if the denominator is 0. Denominator equals to 0, because then the whole fraction is undefined. Denominators equals to 0 if x squared minus 2x equals to 0, because 3 is always 3, constant. When we factor out x, we can see x equals to 0 or x equals to 2. 0 and 2 are in the domain. That means they are also a critical number, 0 and 2. And let's actually see what's happened at 2 and at 0. We may maybe not see, but we do have vertical tangent. Yes, vertical tangent. And of course, derivative at 2 is undefined. dne. Also at 0. Vertical tangent and derivative at 0 is undefined, because vertical tangent doesn't have a slope, no derivative. And we knew, because 0 and 2 came from that condition. But they are still important numbers, critical numbers. And 1 came from horizontal. Okay, that means all of them are critical numbers. Let's put the final answer. Critical numbers are x equals to 0, x equals to 1, x equals to 2. Beautiful. Okay, that means that's the way to solve question like this. Finding a critical numbers. One more time. We have to find out where the derivative is 0, where the derivative is undefined, and then always check if these numbers are in the domain. They are in the domain because all of the numbers were in the domain. Okay, that's it. And again, this question is only testing a critical numbers. The next video, the next concept will help us, because we need another like test, another definition, will help us to take these critical numbers and identify explicitly if function attains local maximum or local minimum. From the graph, we see the situation, but not like explicitly. Of course, this is local minimum at 1. Actually, I did state this, but on the graph, okay? Okay, thank you, enjoy this. That means please know the extreme values, what kind of extreme values we have, and the definition of a critical number. Okay, thank you. Of course, I have more examples, you can check. 7 of them, I will recommend solving all of them, finding a critical numbers of all of the functions. You can check the notes. Okay, thank you.